All right, so we're recording. So now let me hand things over to group 441H, Bioraptor.
So hi, everyone. I'd like to start off by saying thank you for coming to our senior capstone final design review. To introduce ourselves, my name is Chloe.
I'm Ireland.
My name is Michael.
I'm Alex.
I'm Jose.
I'm Jonathan.
And I'm Ethan. We're Team 441H, and we have designed the Bioraptor shaker table. Now to cover the contents of our presentation. So we'll be going over our hedgehog concept, value proposition, product specifications, provide a few demonstration videos of our prototype, go over our full design, and then go deeper into some of the design's key features, the risk analysis, design changes we made along the way, and future work to be done on the design before we finish up with time for questions. Now to get us started, Alex is going to cover our hedgehog concept.
Hello, everyone. My name is Alex, and I'm going to be covering the hedgehog concept today. So generally, the hedgehog concept, is a simple concept which wants to show the intersection of three main concepts. This leads to a central, deep understanding of what our project does, the Bioraptor. Furthermore, it allows us to plan ahead and take our product from good to great. First, I want to cover the first circle there, which is passion. So our team is passionate about contributing to the advancement in research here at University of Florida. We strive to help UF research labs become more vertically integrated by providing self-designed shaker tables for their future research. We would like to use our degrees to provide simple and reliable motion for UF Gator researchers so that they can focus on what they do best, researching cell cultures using their biology degrees. The next circle is skill, or another concept. Our team's biggest strength is most likely the numbers that we have, which allows us to have a wide variety of expertise in certain areas. For instance, mechanical concept design, electrical concept design, and software design. This allows us to have a strong integration of systems into a user-controlled interface, which is seamlessly operated, it's frictionless, and it's easy to use. Next, we have economic sustainability. Our concept for economic sustainability ensures that we have affordable cost of production. This is done by having mostly OTS parts. Everything that's not off the shelf uses minimal subtractive manufacturing, which allows us to keep costs low. And other components are done using additive manufacturing, which is easy for replacement and allows us to have rapid prototyping abilities. So bringing that all together, that comes to our design, the Bioraptor, allows us for overall to have a cheap manufacturing cost. We have a strong engineering team and unique operation modes. We have 3 selectable orbital diameters, which allows for the 3 patterns, linear, orbital, and double orbital, all while utilizing only 2 motors total. Continuing on, we have images as you see here. It shows the cost-effective, minimal designed interfaces and actual motor housing assembly. As you can see, there's additive manufacturing, 3D printing on the right, and there's a lot of OTS parts on the left, resulting in the easy-to-use control panel and device for our UF Gator researchers. Next, I'm going to throw it over to Chloe to talk about some product specifications.
So the product specifications outline the performance objectives, specifically the 3 shaking patterns visualized here. The first one is a linear shaking pattern, and our table was able to achieve a speed of 160 cycles per minute using 1 single motor. The second one is an orbital pattern, and our maximum rotational speed that was achieved was 350 RPM using a different motor, and a diameter adjustment slot mechanism was used to change the orbit diameter from 15, 30, and 45 millimeters. The last one is a double orbital shaking pattern, which was achieved using both motors simultaneously. And the maximum speed achieved was 130 cycles per minute. Next, I'll demonstrate our shaker table going through each of the shaking patterns. The first one was the orbital endurance test, and as shown here, the shaker table was rotating at its maximum speed of 350 RPM. Second one was the linear endurance test, and our shaker table was able to move at a maximum speed of 160 cycles per minute. And then here for the double orbital endurance test, our shaker table was able to go at a maximum speed of 130 cycles per minute. Next, we'll discuss the mechanisms of our full design.
So for our full design, our main goal was to make as simple of a design as possible while keeping it nice and cheap. The main reason we wanted to keep everything as simple as possible is to provide the smoothest motion we possibly could for our table. We accomplished that goal firstly through a 2-bar linkage mechanism. So this mechanism went to provide the actual motion for the linear pattern. And we accomplished this with a 2-bar mechanism linked to the motor and a clevis that was hooked up to the main carriage. So this 2-bar link was connected in the middle and then obviously to the motor and the clevis. So that motion of the actual carriage itself was provided by a rail and carriage mechanism. So sitting on that rail and carriage is our full motor assembly for our rotational motor, which actually provides the rotational motion for the orbital and double orbital patterns. We are able to adjust our diameter through a diameter adjustment slot. We'll be going into the specifics of that design a little bit more here in a little bit. Then finally, the actual motion of the table was made achievable by the enclosure of the system. We actually had the shaker plate move on top of the enclosure to ensure that we had as smooth a motion as possible. And all the while, the shaker plate is held in place through a pin connecting to the diameter adjustment slot. So a little bit more about the full design.
So here's a representation of our finished physical design artifact. We have our prototype, which includes a control panel featuring our safety components, and then the various buttons to select the different shaking patterns. And on the right-hand side, we see the shaker table along with the linear motor mounted on the bottom plate. Excuse me. And on the bottom plate of the enclosure, and the orbital motor mounted vertically on the rail and carriage mechanism, directly driving the tray table. Next, we'll discuss the main sub-assemblies, starting with the 2-bar linkage mechanism.
So as Chloe mentioned, the first mechanical feature of our design I'd like to highlight is the 2-bar linkage mechanism. This subsystem enables our design to translate the rotational motion of the NEMA 17 stepper motor mounted to the base plate into the necessary linear motion of the shaker plate. This is necessary not only for the linear shaking pattern, but the double orbital pattern as well. Through our iterative design and testing process, it was determined that in order to have the linear range that we wanted while maintaining a height that would not be impractical to integrate into the given microbioreactor dimensions, a slot was needed in the base plate to enable full rotation. Spacers were added and modified between the motor and clevis linkages to properly align the components and provide the smoothest motion possible. And the clevis and motor linkages are highlighted on the slide. The 2-bar linkage connects to a threaded clevis rod that screws into the orbital motor mount, joining the orbital and linear subassemblies. Next, I'm going to cover the rail and carriage mechanism. So along with the clevis, the rail and carriage system is the other mechanism necessary to integrate the linear and orbital rotation subassemblies, as well as the homing process with limit switches placed at the ends of the rails. As the 2-bar linkage provides linear motion, the orbital motor and the shaker plate mounted above it is able to translate along the rail atop the carriage its mount is fastened to. With both motors engaged, the double orbital pattern is made possible. This OTS rail and carriage set was selected as the polyethylene sleeve bearing carriage and ceramic coated aluminum guide rail should have a low enough coefficient of friction that it would not require lubrication. This is beneficial to our client as it does not introduce additional substances such as grease or oil that could contaminate or react with whatever is being shaken on the table. And now for Jonathan to cover our diameter adjustment slot.
Thanks, Ethan. So while we were designing our shaker table, one of the main challenges we had was designing a fully adjustable diameter adjustment mechanism. And so what we ended up designing is this black piece shown at the center of the 4 pictures. So the black piece has 3 slots cut out of it. Currently, the pin would be in the largest diameter slot. And if we wanted to adjust the diameter, we could do this through the programmed settings. And so the way this would be done is from the home position, which is on the left, we would rotate the orbital motor 90 degrees clockwise to slide the pin out of the 3rd slot. And then we would rotate the linear motor to translate the pin to the 2nd diameter slot. And then we would rotate the orbital motor again 90 degrees counterclockwise to then slide the pin into the 2nd diameter slot. And in doing so, we can fully adjust the diameter through just the controls of the software. And next, we will talk about the enclosure design.
Our enclosure was designed in order to cover our linkage system and motors, with the sides open in order to ensure that the linkage system is working properly. The shaker table will be placed on top of the enclosure so that it'll be able to shake freely and without any obstruction. And in order to allow the linear and orbital motion, a slot was cut open on the top side of our enclosure, which allows movement of the plate. Moving on, we'll be discussing how we made our shaker plate. Our shaker plate was designed with acrylic material in order to allow for future testing with ODFI. In order to connect to our orbital subsystem to allow shaking, a pin slot was cut into the bottom of our top plate in which it will connect with our orbital subsystem. Finally, to ensure that the shaker plate doesn't become a projectile, it'll be held down by 2 prongs placed on opposite corners. Moving on, we will discuss the fabrication process.
To meet our rapid prototyping deadlines while iterating the model based on testing and observations of the mechanical functioning, or at times the lack thereof, as we went through the design process, non-OTS components were primarily fused deposition modeling printed out of PLA and PETG. This includes the links and spacers in the 2-bar linkage, the orbital motor link, the carriage hard stops, and the shaker plate. However, due to their size and geometry, the top and side plates making up the outer enclosure, as well as the base plate, were cut to size from a sheet of plywood. Hole placements were marked based on the SolidWorks drawings, and tap holes were drilled. Additionally, the orbital motor mount was custom machined from aluminum tube stock, with mounting holes to fasten to the carriage, a slot for the motor shaft to slide in, and a threaded hole on the side for the clevis to screw in and connect the orbital and linear subassemblies. Now to discuss the homing process.
So to do the homing process of our machine, we use 2 limit switches, which are shown in this picture, along with a rotary encoder, which is not shown. So the homing switches will determine the 0 position of the linear motor, and the rotary encoder will be used to 0 the orbital motor. So if we go to the next slide, there's a video showing the homing process. And this homing process was added to all 3 motions, all 3 shaking patterns. So it would be done before the linear shaking pattern and before the orbital and before the double orbital. So that was kind of what was shown here. The way this homing process works is the linear motor rotates until the carriage slides into the limit switch on the right. And then once it engages the limit switch, it'll counter rotate 4 steps in the opposite direction, which will essentially set the motor to, or the carriage to always start in the same position. And next we'll talk about the control interface.
Our control interface consists of a display screen, which prompts and guides the user through the shaking sequence from turning the system on through the selection process, shaking, and shutdown. And then 3 buttons correspond to each possible shaking size as made possible by the diameter slot adjustment mechanism. 3 other buttons correspond to each possible shaking type. As you can see, one is not pictured here because it was not installed at the time. And then an LED light to indicate that the system is turned on, a power switch, and a mechanical emergency stop. Also not pictured here is our potentiometer used for speed selection and adjustment. And this addition to the control panel is part of our future improvements. And next, I'll go into a risk analysis. So in order to identify the appropriate redundancies to add to the system, a risk analysis was conducted. And the 3 biggest risks include the loss of control of the orbital motor on its rail and carriage during linear shaking, loss of communication with the Arduino, and also loss of communication with the motor controllers. And on the next slide, this led to the inclusion of the following safety features. 2 normally open limit switches were placed on both ends of the rail and carriage. During nominal operation, the motor should not hit the limit switches because they are out of range of the maximum shaking radius. But in the case that an emergency were to happen, the limit switch would be closed and it is written in our software to stop all functions. The emergency stop button is wired in between the power supply and the Arduino so that the user could cut power immediately if necessary. And then also not pictured here are the heat sinks that have been placed on the motor controllers, as well as a fan that will be included and pointed at the electrical components while operations are in progress. Next, we'll start discussing design changes, beginning with the mechanical design changes.
All right, so to discuss the mechanical design changes, the largest change that we experienced overall during testing was the removal of an entire system that we initially designed. So this entire system was called the hinge system, and its purpose was to stop the rotation of our table along the vertical axis while it's actually in motion. So the reason why we removed the system is that during testing, we found that not only did it not restrict the motion in that vertical axis, but actually prevented the table from moving correctly and moving in a pattern that we deemed as smooth enough to actually pass for us. So because of this, we had to make a decent bit of other changes for our design. So one of those changes that we had to make to our design was removing the adapter for the actual hinge connection on the shaker plate. So that's actually where the hinge system would attach up top to the shaker plate, and that adapter was removed, and it allowed the shaker plate to be manufactured much more easily. A change that was made that didn't have to do with the hinge system was the actual spacing of the 2-bar link and the motor itself. So the reason why this was done is during testing, we saw that the actual spacing of the motor and the links didn't allow for the motor to make a full rotation during the actual linear shaking pattern. So because of this, we redesigned the links and we redesigned the spacing to allow for the carriage to make that full rotation. And with that, I have 2 more mechanical design changes to discuss. So the first of these other 2 design changes that was made was the removal of the slot in the enclosure for the hinge system connection. Again, this change was made due to the complete removal of the hinge system. This will also help with the simplification of manufacturing for this plate. We'll be able to get it done in much less time now. And finally, the last mechanical change that we made was different sizing, different holes, and different locations of mounts in the base plate itself, as well as a slot cutout to allow for the 2-bar link system to move properly. And due to this, we were able to successfully move in the full rotation for the linear motor. And with that, we can start discussing the electrical design changes.
So there were 4 main electrical design changes that were made during prototyping and testing. So first, we swapped out the Pololu 84988 motor controllers for the TMC2208 motor controllers. The reason being the TMC2208 uses a smooth sinusoidal signal instead of a square wave signal. And this just allows for smoother motion of the motor controllers. We also changed, we repurposed one of the buttons. Originally, it was used for the 4th orbital diameter selection, but since we reduced our orbital diameter selections to 3, we repurposed that button to be used for pattern selection. So it was now used for the orbital shaking pattern selection. The third design change we made was changing the Arduino Nano to an Arduino Mega 2560. This was done because during testing, we fried the Arduino Nano and there was no more available. So then we had to adapt all our electronics to the Mega 2560. It is important to note that our components would still all work with the Arduino Nano, should those be available. And there's also perf boards that are soldered with the Arduino Nano in mind. Moving on, the 4th design change we made was a rewiring of the e-stop button and the power button. So originally the e-stop was wired as shown on the left, or it was planned to be wired as shown on the left, but then we quickly realized that if we wanted it to act as a hard stop, it should, or as a mechanical stop, it should be wired directly after the power supply. So we made that change so that the e-stop could be pushed and cut all power to the system. There's also a power on and off button, which was added just for visualization to easier determine when the system was on or off. And next, we will talk about the software changes that were made.
So here are some of the changes made to the software. Most of the changes came out of testing and fine-tuning the responses of the system to the commands that are written in the software, as well as adjusting for electrical system changes. This includes the scaling of the linear motor steps per revolution magnitude. And this was just due to the motor controller in use, and we discovered this through testing. Another change was that an additional button was included for the shaking type selection, and so we needed to add an additional pin assignment as well as assigning it as an input pin, and this just simplifies the user interface. Another scaling change that was made was the motor speed, and this was just because the motor response to our speed command originally did not equal our user's input, and the scale factors were discovered through testing, as well as the potentiometer resistance range mapping to our speed range. We originally had an incorrect range, and we discovered the true range during testing. On the next slide, I have a few more changes. So the potentiometer speed selection display, we made this easier to read on our display screen. Originally, it was shaky because as the computer looped through the code, it was reprinting that value. So we used a string function to only display the speed as it's suggested once as the user is changing the potentiometer. The shaking selection sequence was also reordered, as well as the homing structure, which was put into its own home loop structure. And these changes just simplify our code. And we removed our emergency stop sequence because we changed that to a mechanical e-stop button. The limit switches are already a software emergency stop, so this just adds a redundancy in case communication is lost with the Arduino or motor controllers. Next, we'll go over a cost table summary.
Our shaker system came out to about $630.27, with the majority of our cost, approximately 80%, coming from our off-the-shelf parts. The remaining 20% of our cost comes from our manufacturing cost, which came about around $139.06. These manufacturing costs include creations of our enclosure and our diameter adjustment slot mechanism and other things of that nature. Moving on, we'll discuss how we can further improve our design in the future.
So some future work that needs to be focused on mainly are all centered on both making sure our design meets all of the customer needs and conducting more holistic sequence tests with all of our intended hardware integrated. And then once we have a fully fleshed out design, we can make the presentation improvements that will take us from a testing prototyping stage to having a final usable product. And with that being said, this concludes our presentation of our BioRaptor shaker system. Thank you again for all of your time and attention. And at this time, we'd like to open up the floor for questions.
Okay, sorry. I was mid-chew there when you guys wrapped up. So, all right. So, are there any questions from our panelists? We had Alex Lacerna jump on as well a little bit after we started. Okay, if not, I guess I can jump in to start. So I had there was one sort of glaring moment in my looking through your video. So you guys had you're showing the motion of the various shaker patterns. And there was one, and maybe I'm imagining this, but it looked like the well plate actually like fell off in the middle of the shaking test. Did I see that right, or is that sleep deprivation?
So the well plate, I think you're most likely talking about the double orbital shaking test.
Yeah.
In that one, the well plate actually counter rotates as the orbital motor rotates. Essentially, it's counter rotating due to inertia, but it's still fully attached. And it remains flat in the horizontal plane.
Okay. I probably need to see it again. Would you mind going back and maybe we could play that video again? Yeah, I think that was it. So.
The foundation of the entire device is a little rocky, so that might have been what was causing it.
Okay. Yeah, it's very wobbly. I guess it didn't come off completely. But yeah. Oh.
Yeah, it won't come off because we ran it for over an hour, so it won't come off. It just kind of rotates like that.
And okay, so is that a feature then that you actually want it to counter rotate?
No, so that's what we were trying to prevent with the hinge system, but with the hinge system itself, there's really no way we can get it to move properly. So in order to stop that, we would have to have I don't want to say a large redesign, but it would take more time than we had to add in a new system to prevent that rotation.
Gotcha. Okay. And then actually, this is a good, like, while we're here. Oh, hang on. There's a question in the chat. So for the purposes of the video, let me just read it. So Devanji is asking, have you looked into some dynamic stability for the shaker table?
Yeah, so one idea that we had as a solution to removing that twisting degree of freedom there, because our hinge system didn't restrict that twisting. It was still twisting about this loose sort of fitting that we had. We were thinking of potentially adding magnets to the enclosure top plate, and then as well as to the bottom of the shaker plate that holds the well table, and creating like a small electromagnetic field that it wouldn't move out of its sphere of influence, I guess, while it's doing the shaking. But we didn't have any time to do that integration or testing, but that's one of the ideas that we had for that.
Okay, and while we're here, actually, this is a good view as well. So the oh, excuse me, lunchtime. The video that you showed, you've got the outer housing made out of, I think it's like wood, right? Like, or, okay, everybody's nodding. Okay. And then, yeah, there we go. It's made out of wood. And then is that the final material choice, or that's just for prototyping?
That was for prototyping. We had some later, some later design iterations that drastically changed the sort of enclosure and base plate designs. And because we were making those modifications on those parts, we just couldn't get them in the manufacturing queue in time to have them ready.
Okay. So you guys made the wood pieces yourself then?
We did.
Okay. All right. Oh, your friends are turning on you. Okay. So we have a question from Andrew. The 2-bar linkage extends out of the bottom of the housing. Any concerns about safety with the linkage catching on anything underneath it? Maybe in case the bottom so nothing can get in there.
Yeah, that's definitely something we noticed while we were doing testing. And one of our improvements we want to make eventually is just wiring organization. That was really the only thing that we saw getting in the way of it. But just through testing and a lot of our hardware, unfortunately, being damaged, we were sort of still in our breadboard wiring stage for a lot of this final demonstration testing. But yeah, that's definitely something that's been in our minds and we've observed it.
When you say hardware being damaged, you're talking about like frying your controllers and your motor
The
drivers.
controllers, the Arduino that we originally had. Yes.
One computer.
A computer.
Oh God, you guys were the fried computer group. Oh man. Okay. Lots of electronics going up in smoke. Oh man. Okay. All right. Ugh. So Andrew, did that answer your question? Okay. Yeah. He says that all makes sense. While we're here, this was another image that kind of caught my attention. So, and I wonder if I can annotate. Yes, I can. That's what happens when you make me the co-host. So, so there's like this. There we go. Like this little leg, that's definitely providing support, right? So there's like force pushing up on that leg, but it's basically like a cantilevered beam, in close proximity to a motor, which is probably vibrating as it rotates. But then also, like as we saw in that previous video, like the whole system is kind of like wobbly, right? For lack of a better word. Is this like a problem? Like why not just close that off? So this isn't just I'm worried that this piece here, the cantilevered piece, is gonna vibrate all over the place and make your wobbly vibration worse.
If we were to keep that slot going forward, we probably would extend the base plate out just to have that end closed in and not have it as a beam. We had the base plate cut already when we determined that we needed the slot. So we cut the slot in what we had just to, keep iterating quickly.
Okay. So I'm getting kind of a common theme, which is you guys had dreams. You had a lot of kind of visions, but I'm hearing a lot of, well, we ran out of time and we couldn't implement things. Can you talk a little bit about that? Like how did time or lack thereof kind of influence what you guys ended up with?
I'm sure other people want to speak to this too. I think our biggest thing was in the beginning trying to get a fully fleshed out, completely checked out design. As we started to move through our rapid prototyping, we made a lot of real life response discoveries, and we just were constantly iterating, making changes, implementing different components. And so it ended up, I would say that is sort of how we got to where we are right now.
That, and combined with the electrical issues that we experienced, which were very unfortunate, but our first actual test where we were fully able to run both motors, run the full system all put together, was the weekend after the first performance test was supposed to be. So I want to say we had about a week and a half of trying to prototype it after that first test session. And it was just an unfortunate thing altogether.
So did you guys, given the lack of time, did you guys get through the endurance testing?
We did, yeah.
We did.
Submitted all of those.
Okay.
Yeah, we finished that yesterday.
Okay. Got it. So another kind of big question. So one of the nice things about having everybody in the class work on the same customer needs statement with the same basic problem is we get to the end, right? And you can actually see like what designs worked and which designs kind of didn't. It's an opportunity. It's a teachable moment that doesn't normally happen in a conventional capstone course. It happens in UFME capstone because of the way we do it. So clearly you guys had problems with like time, with exploding electronics, fried computers, but fundamentally, do you believe in this design? Like having seen like all the other possible ways to solve this problem from the 14 other groups, and I asked this question. Alex is in here, so he can speak to this. I asked this question of a previous group, and I think the question came across as sort of like a loaded question. And it's not meant to be. What I'm really asking, and I really want your honest assessment, like, do you guys believe in this? Or having gone through this, would you do something different the next time around?
I would continue to do this design just because of the way that we see it. Is we think that this is a very simple way of doing this design. We do have multiple ideas. If we were able to prototype for, let's say, another week and a half on top of the week and a half that we already did, if we were able to manufacture another base plate, we believe that we could get something working perfectly, or well, maybe not perfectly, but capable of performing the same orbital patterns that we were capable of doing, but just limiting those few issues that we had with this design.
To tack onto that, I think in some of our tests, we witnessed our design running a lot smoother and a lot cleaner than what we were watching other people's designs do, with much nicer parts that had gone through the manufacturing queue, were made out of metal, were as they exactly intended them to be designed. With some of those tweaks, I think we could have gotten things even smoother than they already were. Our orbital pattern was almost silent when we were running it.
Yeah, you guys don't have any. Sorry to interrupt you. You guys don't have any motor reversals, right? Your motors just spin.
Yeah, there are no motor reversals, which I think is one of the strongest points of the design.
Yeah, we're finding that the motor reversal shaker tables are really loud, and the ones that are not reversing are quieter, and the loud ones are loud enough. Juliana's not in here, but Juliana, you guys know Juliana. Juliana, I'm sure she sits in the lab all the time. She's one of the MEC 2 ULAs. She actually commented, she's like, it's too loud to even think in this room with all the shaker tables running because they're so loud. And I'm like, yeah, they are. So like the loudness of the direction reversal solutions would probably prevent those from becoming real commercial products, right? You can't imagine sitting in a biolab and having this racket 24/7 for 2 weeks as the shaker table is, doing its thing and just making this noise. So, so along those lines, given that you do not have any motor reversals, did you even need stepper motors? Could you have gotten away with just brushed DC motors or even brushless DC motors?
We Here, I'll take this one. We could have for the motor responsible for the linear pattern. We couldn't have for the rotational pattern solely because the stepper motor, or it being able to go in both directions, is what permits it to change diameter without somebody actually like going in and touching it and like picking up the table like completely separate from everything else.
But a DC motor you can run backwards. You need more than just the ability to run it backwards. You need to be able to run it backwards a set number of steps so that you can move the pin. Okay. We're at the end here of Mech 3, and where all this goes is just like you guys did at the beginning of this semester. We're going to gather up all these designs and we're going to give them to the next semester's Mech 3 students, and those guys, their job is going to be to take your designs and to basically harden them so that they can run in a freezer or in an oven to meet the temperature range requirements, and then also add ODFI, optical density and fluorescent intensity capability. So like what I worry about, because I'll just, we're recording here, so for posterity, I think you guys are right that this design it could actually be one of the more competitive designs because it is very simple. It doesn't require motor reversals. I think you guys are the only ones that had something that was like this. Almost everyone else is using belts or rails, or something. Not that you guys have got that one rail, but like a lot more extensive rail systems. So I think this one has the potential to move forward. But when the Mech 3 students next semester see it, they're going to see this like, okay. Ethan's laughing. So you guys get what I mean, right? It's, for lack of a better word, it's kind of kludgy right at the moment. So how do we convince next semester's Mech 3 students of the value of pursuing this as a possible system for them to adopt and run with next semester?
I can kind of go into this a little bit. The remaining problems that we have are very solvable problems. Restricting that twisting degree of freedom, that's just going to take a group of people, in their brain power, adding some extra analysis. The speed issue, we probably just need to, organize our wiring a little better so that transfer of data between our Arduino and our motor controller to our motor, is fast enough to, get our speed to meet the customer needs. As far as presentation improvements, that's something that I think even our team would have been capable of, given, like Michael said, an additional few weeks. So I think all of those problems are not things that, a future group of students are going to not be able to figure out, within the first two design milestones. If anyone else wants to add.
I'd also like to touch on just the fact that we were able to bring the idea, the concept up to where it is now, which is like 90% of the way there. The last 10% is probably going to involve a lot of that theoretical analysis. For instance, probably a lot of tolerance loops within that linkage design. But once those are kind of fleshed out, I think that there is potential in having it run almost silently, being very smooth. And honestly, a lot of the work can be done within the software code itself, because having both motors go in the same direction, it's all about just timing of those steps, exactly where we want them to be when we want them to happen. I'd also like to touch on your point about it being laboratory research ready. I think the slim form factor allows you to have 5 or 6 of these in a row along the same workbench without it really taking up too much room. And the fact that we already have it, or have demonstrated it being kind of silent or quiet at some times, maybe not all the time, it has definitely some legs that can get it running.
To Alex's point, he wasn't there on the last day of testing, but on the last day, we kind of figured out that if we use smaller step sizes on the motors, it performs even quieter. And so on the last day, it was pretty silent. As far as linearly and double orbitally, it was pretty silent when it was running. just an update for Alex, I guess. But yeah.
Yeah, we should, I don't know if all you guys are graduating and leaving, but we should have, somebody from your group come back next semester and, pitch this one a little bit, because I worry that the groups next semester are going to see the design and just be like, oh, it's not really well fleshed out, and it'll sort of get lost to the house of quality process. So, okay. I had one more question and I lost it. One more question. Oh, okay. DG saying you have to run to class. Great work. Simple design, managing a working model. Oh, which reminds me, with a computer disaster. Thank you. Okay. Thanks, DG, for popping in, and send me your evaluation, just an email.
Yeah, I'll do that. Good job, everyone.
Awesome. We miss you. Come back.
I want to.
We want you back.
Bye.
So, oh gosh, I just had it, and then what she said, energy working with
Something about the computer
no, it wasn't. Oh, I had it on the tip of my tongue. Oh,
or
well.
working model.
Oh
Those
yeah,
are the
yeah,
two
yeah,
things
yeah.
with
Okay, I got it. So so Rick Miles from Northrop is not here, but I'll sort of echo a comment that he made to another group, or well, maybe turn it into a question. So what we're finding, to our surprise, he actually wrote me this in an email. So you guys have survived Mech 2, right? Where we at least attempt to try to convince you that it's a good thing to do analysis and orientation calculations, and really kind of settle in on a fully functional final design report, on paper design, before you jump into prototyping. What we found, and I think this is true of your group as well, is that teams sort of did a little bit of that, and then they jumped in to what back 1,000 years ago when I was a PhD student, what my advisor would call an Edisonian approach, which is, if you know the story of Thomas Edison and the light bulb, he tried something like 10,000 different filaments before finally settling on the one that ultimately became the patented, General Electric light bulb. And I'm also getting that sense from you guys that you sort of had a what is it that Mike Tyson said? You have a plan until you get punched in the face. Like, you guys had a plan, right? And you sort of implemented it, and then very quickly it became, well, this doesn't work. This doesn't work. This doesn't work. Let's just try these other things. And how much, once you built the prototype and it was clear that it had some issues, how much of what you did after that was, let's go back to the drawing board and do more orientation calculations and kind of redesign this thing on paper, and how much of it was, let's try 10,000 different light bulb filaments and just pick the one that works?
I think I probably did the most of this out of everybody. So we started with a full model, and as we started on our initial prototype, we started to realize that there were some issues. And so we made, like, initially just a few design changes that really changed the direction of the model. And then, so once we made those, it became not so much trying a bunch of different things, but using the prototype where it was to then determine what we needed to make it work. So, measuring the gaps between things to size spacers, changing the lengths of the links in the 2-bar linkage to get that to line up correctly and get the linear range that we wanted.
Okay, so this actually became more of an experimental test rig than a final
Absolutely.
functional prototype. So Chloe, I wrote that in your recommendation letter. So okay, that makes sense. So
I'd also like to add there to Ethan's point that even from the the birth of the idea, the concept, we've had challenges pretty much every single time we met. So there was always a wall to get through. Some of them were a little thicker, probably made out of brick, and others, very flimsy, but that's like just in general. So none of the answers are really trivial, like sticking out at us, but it kind of just became natural that every time we were meeting, there would be a challenge to overcome. And there really was, there were a couple walls that were a little bit there where we were like, all right, we should go back and switch. But in the end, like we realized, oh, every problem we've encountered so far has been surmountable, and we just continued going with that that mentality.
Yeah. So this is actually pretty interesting, and I realize we're over time. So you know, if you guys have somewhere else to go, class starts at 4:05. You can feel free to hop off. But kind of my last comment is I think the way that you guys approach this is much more like researchers, much more like what graduate students are expected to do, rather than you know, junior engineers starting at a company, which so I'm a big fan of both. So I, you know, of course I, you know, did grad school and got the degree and all that stuff. And, you know, kind of understand, at least I think I understand, I pretend I understand how the research enterprise works. And this approach of, I like this idea of you guys, once you realize that there were these problems, you kind of use this as an experimental test stand to identify and solve those problems. I think that's a fair way of going about doing it. It's not what we teach in Capstone, right? We teach in Capstone more of what you experience in Mech 2, which is you sort of stop and you go back to the drawing board and, like, you know, redesign things on paper. But I think that this is your approach is an equally valid approach that would be much more geared to a successful end product in an academic environment than maybe an industry environment. So there's nothing wrong with what you guys did. And actually, now that I'm sort of thinking through it and hearing your descriptions of it, it explains a lot about why this thing is the way that it is, right? Like you guys, instead of like, you know, let's like build it out of metal and like it's like no, let's build it out of wood and figure out, like, you know, how to make it better as an experiment. And then just time caught up with you, right? You guys basically ran out of time to be able to implement everything that you had discovered through all your experiments. So that's an interesting, that's sort of a deeper, like, pedagogical, like, are we actually teaching you the right way to solve these kinds of problems by giving you the Mech 2 approach instead of a research approach?
If I could add something to that, one thing I noticed coming into this class, being a senior, having had a few internships, the things that I now can, you know, imagine in my head that would actually work are definitely more complex than they were several years ago. And still, you know, during the analysis part, I wasn't able to foresee so many of the small, you know, oh, there might be a vibration mode between that pin and the slot in our shaker plate. And that needs to be specifically, you know, we need to do analysis on that. Or the alignment of the 2-bar linkage mechanism. If it's off by this amount, you know, we need to do analysis on that because then it's not going to work or it's going to be really noisy. And I think had we had those issues in mind, if we had done the heavier analysis, we probably could have avoided a lot of our research style prototyping process that we did go through. Despite having not done that, I think on our next projects, whatever we each go and do, we'll avoid even more issues at the stage that we did with this project. So
Yeah, no,
Yeah.
there's a lot to be said for like experience, right? That's like when I was a grad student 1,000 years ago, my master's advisor was this 85-year-old dude who, like, for some reason still hadn't retired, even though, you know, retirement age was like 65. And just the scope of things that he had seen in his career, his 60-year career as an engineer, made him just an absolutely invaluable asset, right? I mean, you know, okay, he slept half the day, but also, like, he had seen like everything, right? So if you could manage to wake him up and ask him a question, he's, oh yeah, I saw that in, you know, 1964, I was doing something other. And so yeah, I think the experience that you guys gained, I mean, ultimately at the end of the day, this is a class at a university, right? We try to pretend that it's not, but I think you guys probably learned a lot more than maybe most of the other groups from kind of doing battle with this thing all semester, rather than just having it like work the first time right out of the gate. So in a way, you know, even though you've got that video of the well plate kind of, you know, shaking around on the top, which looks a little, you know, amateur-ish. Yeah, this video. Yeah. Yeah. I think you guys learned a lot, and I think that this experience will be beneficial when you guys move into the next phase of your you know, careers or grad school or professional practice, because this is one of those like what is it, Murphy's Law? Anything that can go wrong will go wrong. I feel like you guys like lived that this semester.
Yeah, if I could just add to
Definitely.
that too, really quick. I mean, I've also watched you guys work a lot throughout the semester, and I saw a lot of the design evolutions. And I really think that you guys were the team that went through the most number of like significant redesigns from the initial design phase to the actual manufacturing and testing phase. And I just want to compliment you guys actually for really, you know, keeping your heads high through all of the different challenges that you faced. I mean, for crying out loud, one of your computers fried, and you guys are still on here with smiles, and I just really think that's incredible. So good job this semester, guys.
Yeah, very good. Okay, so I've gone way over now, and I'm looking at the time and realizing that we're supposed to be in another design review right now at 4:05. So I think probably that's a good place to wrap it up. But yeah, let me just echo Alex's comment that you know, you guys showed an enormous amount of grit and persistence, and you know, willingness to not give up. And I'm even though I asked you the question that I said was sort of, you know, maybe a loaded question about would you pursue this if you had to do it over again, I get the sense that you genuinely feel like you would, that this was in fact the best design, and you were just sort of the victims of a series of unfortunate events, which, you know, to some extent is valid if like smoke is billowing out of your laptop computer because you zapped it with 12 volts. So I get that. So yeah, I really, you know, just appreciate that you guys stuck to it and you didn't give up. And in the end, you produced something that if not like, you know, a viable pre-production prototype, it at least you guys use it as a teaching tool to learn how in the next iteration you could get it to that point where we wanted it to be, right? Instead of you know, just sort of throwing up your hands and saying Mech 3 is hard, I hate Trom, like, you know, you guys stuck with it. So I appreciate that. And there's a lot of value there in what you guys got out of the class and the experience. So anyway, on that note, let me stop recording.